All right, 4.8 is going to look like a lot of review for part of it. Part of it is going to be a little introduction to some new material. But we're talking application of trig functions. So going back to like what we know about our right triangle trig, sine, cosine, tangent, how can we make those work for us to answer some of these real world questions? One of the things in this section is the idea of solving a right triangle. All that means is when you're solving a right triangle, you're finding your missing information. And you have to be given 3 pieces of information to solve a right triangle. As you can see in this particular example, we've got a right angle at C. At angle A, we've got 34.5 degrees. And then we've got side little b as being 10.5, which means we have 3 unknowns as well. We've got angle B and then our 2 missing sides here. So first of all, if this is what's set up for us, you can always remember that angles add up to 180 degrees. So I can start by taking 180 minus what we know. Angle C is 90, angle A is 34.5. And when I get that, my answer for angle B will be 55.5 degrees. So there's 1 out of our 3 missing pieces of information. This is not necessarily the best example for this, but I would always go back to my picture here and say, okay, what information do I have? And use that instead of information I've found to find our missing side. So like if I'm going to find side A, I would use the angle that I already had, the 34.5. I'd use the side B that was already given to me, that was just 10.5. And compared to angle A, this would be considered an adjacent side. And the side I'm trying to find right now, we'll try to find A, would be the opposite side. And so then I think through my SOHCAHTOA and find the one that will work for me to find that uses both opposite and adjacent. So we should set up a tangent equation. The tangent of 34.5 equals our opposite side A over our adjacent side 10.5. And I should multiply on this. And we get that A equals 7.22. In the directions, it did say to round our lengths to 2 decimal places, which is why I picked 7.22. And so then our last one here, again, sticking with what we have, and again, not what I've rounded. So I would not use the 7.22 to find anything else. I'm going to stick with what I know, my adjacent side of 10.5 and our hypotenuse, C. So then I find the one that uses adjacent and hypotenuse, and I would set up a cosine equation this time to solve for C. And a cosine is adjacent over hypotenuse. And when it is that setup, remember we would divide. So 10.5 divided by cosine of 34.5. And as you guys are typing this in your calculator, making sure you can get the same answers that I'm getting as we work through our notes. Notice we are working in degrees. So if you are not getting the answers I'm getting, please make sure that the first thing you check is your mode on your calculator and that you need to be in degree mode. And for this one, we should be getting in 15.28. Always keeping things in mind, am I even getting an appropriate answer? Our hypotenuse should end up being our longest side. Your shortest side should be across from your smallest angle, type of things that we know from previous knowledge about triangles. The next part is, again, kind of look familiar. We've done some problems like this where we utilize right triangle trig to help us find some missing information. So next question here, using 2 right triangles to solve a problem. It says you're taking your first hot air balloon ride. Your friend is standing on ground level 100 feet away from your point of launch, making a video of the terrified look on your rapidly ascending face. How rapidly? Well, at one instant, the angle of elevation from the video camera to your face is 31.7 degrees. 1 minute later, the angle of elevation is 76.2 degrees. How far did you travel to the nearest 1/10 of a foot during that minute? So they're looking at how far we travel eventually here. Well, in order to do that, we're going to unoverlap these 2 triangles and look at the lengths that they have marked in that picture as A and B. And the difference between those will be how much you have traveled in that minute. So let's start with the first triangle they gave us. where they call this side A. They said that this was a 31.7 degree angle of elevation, and your friend is 100 feet away. So again, we think through our SOHCAHTOA. From 31.7, A would be opposite, 100 would be adjacent, and so I would set up our tangent. Since it is A over 100, I would end up multiplying, and we find out that the height in that first measurement, the height is 61.8 feet. And so then we look at the second triangle, where they're looking at a much steeper view here, still standing 100 feet away, but this time looking up at 76.2 degrees, and they called that height B. Same, opposite, and adjacent. So again, we're setting up a tangent equation, but our angle of elevation definitely changed. 76.2 degrees is B over 100. And again, I would do some multiplication here and get that our height, the second measurement is 407.1 feet. Okay, so then the question is, how far did we travel to the nearest foot during that minute? Well, our travel during that minute, if we call that maybe X, would be this length right here. And X would be the whole height B minus that little part at the bottom. So if we put those numbers in there, we traveled 407.1 minus 61.8, and that comes out to a total of 345.3 feet. I will tell you that if you did not round at all, if you like just type that all into your calculator without ever rounding, it does come out to 345.4 feet, and that's fine. You just got to show your work. Okay, so on this next one, again, we got two triangles, but a little bit different here. Again, they're asking us to find the length of X. Again, I have too much information. I've got two triangles here. And so what I see is I've got X broken into two pieces. We've got a piece here and we've got a piece here. And together, those two pieces will give us X. So I could, again, call them like A and B. And ultimately, then X is going to be the sum of those. So I need to find what those are separately. Given the two pictures that we have, and again, you're just going to kind of ignore the second picture. I'm going to look at this 40-degree angle first. A would be opposite, 500 is adjacent. So again, I'd set up a tangent equation. And again, the way that's set up, I would be multiplying, and I get 419.5. Similarly for B, in the second triangle with an angle of 25 degrees, B is opposite, 500 is adjacent. So again, I would set up a tangent equation. This time my angle is 25 degrees, opposite is B, adjacent is 500. Multiply 500 times the tangent of 25, and we get 233.2. So then putting all of that together, knowing that the question really is, what is the length of X? We have 419.5 plus 233.2, which comes out to 652.7. They did say to the whole unit, so I would say 653. All right, one more here with using some overlapping triangles, and again, getting creative with how we mark things. The one thing I would say in this one is you again need to consider right triangles. The reason I say that is X right here as is marked. If I were to trace that, I see a triangle, but it is not a right triangle. And so although I know that this is going to be a 12-degree angle, the difference between 40 and 28 degrees, that triangle in there will not work for me to just set up a SOHCAHTOA type of problem because I don't have a right triangle. So we need to overlap these two triangles. Again, the two right triangles that I see is this big right triangle here that has a 40-degree angle, a side of 400, and this side right here, this entire side right here, again, we'll just call that a letter A. And then my second right triangle that I'm seeing in here would be this smaller right triangle that has an angle of 28 degrees. And again, a side of 400, and its side right here, we can call B. So then how does X relate to those two values? Well, it becomes the difference between them. And so eventually, once we find A and B, is that I'm going to take A minus B, and the leftover is this piece up here, which is what they are calling X. So setting up my equations to then solve for A and B again, we consider where our angle is, where our sides are in relationship to that. A is opposite, 400 is adjacent, so we're going to use tangent again. Type that into my calculator, and we find that that length to be 335.6. We do the same thing with our smaller right triangle that has an angle of 28 degrees. Again, it's opposite and adjacent, so I'm again picking tangent. And this time we get a 212.7 for our measurement. So solving for X, find the difference. 335.6 minus 212.7 gives us a 122.9. And again, they said to round to the nearest whole unit, so 123. Okay, the last topic we're going to talk about is the idea of this thing called simple harmonic motion. Simple harmonic motion is something that is very real world applicable, and one of the main reasons that we end up looking a lot at trig functions, because they tend to model real world data quite closely for things that have this simple harmonic motion. Things like the vibration of an instrument, the swinging of a pendulum, the bobbing of an object attached to a spring. If we were to track temperature throughout the year, it rises and falls in a periodic motion. The high tide, low tide of water, all of those things are very easily modeled using trig equations. What you guys are looking at is a picture of a spring that is with a ball attached to the bottom of it. It is pulled down to a distance of 4, released, and then it goes up, and then back down, and then up, and then down. And they've measured it over 12 seconds here and kind of shown where it is at each of those seconds from 0 to 12 in this picture. And what you do if you trace where the ball is located is you end up looking at like a cosine curve. One of the things just kind of on our book specific is they talk about the distance from rest. And so what you can see here is we've got an axis that we would normally call like our y-axis is their distance axis, where 0 would be its resting position. So I have not pulled it or released it, and that's where it would be at rest. And the axis, the next to it, measures how low it goes or high it goes above that resting position. And to us, that would be, as we look back at our trig functions, like our midline, and then our minimums and maximums. And so we can find our amplitude from that, which you're seeing here. So if our resting and they pull it down a distance of 4, that would go 4 below our resting. And so that distance, notice I have them marked in absolute values over here, is our amplitude. It doesn't matter, again, if you're measuring from the minimum to your midline, where it is when it's resting, or maximum. The challenge is going to be that sometimes we have to interpret this from information given to us when they talk about, like, they pull an object 4 units below its resting point. Well, that means that our amplitude is 4. Okay, in our different situations, we will have to decide if we are writing a function as a sine or a cosine curve. And so it all depends on where the object is at time equals 0. And these are pretty much the 3 places it can be at time equals 0. Your object can start at the resting position at time equals 0, and that would indicate a sine curve, because a sine curve starts at our midline and then moves. If they talk about your object starting at a maximum at time equals 0, we would write it as a cosine curve. And if the object is starting at a minimum at time equals 0, it would be a cosine curve, but because of the minimum, we would write it with an ROX, meaning that it's starting at a minimum instead of a maximum for cosine. And again, depending on our situation, it can start in any of these 3 locations at time equals 0. But that little piece of information, where is the object at time equals 0, helps us identify which of those 3 options we would pick to write our equation. So our equation will follow what we are used to. They write theirs as D, so displacement. Amplitude is the maximum displacement from the rest position. And again, might take some interpreting for us, but again, it's going to be how far above and below that resting position it goes. We talked about this on the last page. I put in sine here, but it could be cosine or a cosine with an ROX, depending on where it is at time equals 0. So again, we pick this particular function by where the object is at time equals 0. And then they use this symbol here, which is just a Greek symbol, which is no different than what we are used to being. It's going to be 2 pi divided by that number. So again, period being how long it takes us to complete one full curve, whether that be getting from a maximum to a maximum or a minimum to a minimum, completing one curve, and then the number you'll see in your equation is going to be 2 pi divided by that. Okay, so an example here. It says a ball on a spring is pulled 6 inches below. 6 inches below becomes very important. Its rest position and then released. The period for the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. So the period for the motion is 4 seconds. Again, they use that Greek symbol. Let's go ahead and just keep calling it B. We get B equals pi over 2. Now, what you're going to notice is we were very used to B having a pi in it, but when we're talking real world numbers, it actually ends up being pi more often, because a lot of times we measure in like whole units for a period. 6 inches below, let's go back to talk about that. 6 inches below means we are starting at a minimum. So I'm going to write my equation as a negative cosine, a cosine with an ROX, because it's starting at a minimum, and 6 inches is going to be our amplitude. So putting all of that into our equation, our displacement equation is going to be negative because we're at a minimum, 6 because that's the distance we are below the resting position, cosine again because of the minimum. So I pick this and this because they say that we start at a minimum. And then we're going to put the B value in here, pi over 2, t being our variable. Okay, and then our last vocab word that we're going to get introduced to here is frequency. And this frequency is something we've kind of addressed a little bit before, but this is just a more natural place to talk about it because a lot of times in real world situations, we're not necessarily talking about one complete curve, but more often we would look at like one time period, like in a day, how many times does the high tide rise and fall? Things like that. And that's where frequency comes into play. Frequency says that at 1 unit of time, so on my graph, at 1 unit of time, whatever that time is, a day, a year, a minute, however they're measuring time, but in that 1 unit, how many complete cycles, curves, did we complete in that unit of time? Period is 1 complete curve. How long does it take to complete 1 curve? So you can see I have that highlighted in green here. And then if we follow this, we've got 1, 2, 3, 4 curves in 1 unit of time, which would make our frequency 4. And so what you'll find out is they are reciprocals of each other. That frequency is turning the period upside down, where period would normally take the, like if our period of time was 2 pi divided by how many curves I got in there. They are reciprocals of each other. Now, it is true that F is B divided by 2 pi. I would not bother getting to know that. I would continue to find B the way that we've always found B, 2 pi divided by the period. And then just remember the relationship between period and frequency is that they are just reciprocals of each other. For example, if they say that the frequency is 4, that means that the period is 1/4. Not a lot of work to do between those two. You just flip one upside down and you get the other. All right, last example today is looking at some harmonic motion here. An object in simple harmonic motion described by D equals 12 cosine of pi over 4t. T is measured in seconds and D is in centimeters. It says find the max displacement. So maximum displacement is what we have previously known as the amplitude. How far above and below that resting position we go. And again, amplitude is always that constant multiplier in front of our trig function. And so we would say 12 centimeters because our distance is measured in centimeters. Find the frequency. Well, let's go through what we know. B is pi over 4. Therefore, the period is 2 pi divided by pi over 4, or 2 pi times 4 over pi and 8. Therefore, what we just learned is that the frequency and period are reciprocals of each other. So our frequency is going to equal 1 over the period, or the reciprocal of the period, and that would be 1/8. The last question here is find the time required for 1 cycle. Time required for 1 cycle, the key is the 1 cycle part of it. That's the question of what is the period of this, and we already found that above. And again, reciprocal of frequency, or how we already found that above. So just go to our work above and get our answer. The period of this particular harmonic motion, how long it takes us to complete 1 curve, is 8, and it is in seconds.